In this segment on pointers, we're going to discuss using array names as pointers. When I first told you about arrays, I told you that they were pointers, but not knowing what pointers were, that doesn't make a whole lot of sense. Now it should begin to make a bit more sense. So we know that arrays are contiguous blocks of memory that hold multiple objects of a specified type. In this example, right, I'm creating an array whose name is alphabet. It has 4 elements in it. They're all of type char. Right? And it has an initializer list, so we're storing the characters A, B, C, and D in that array's memory. Right? So the array name then does point to a memory address, the first element of the array. If I use the name alphabet all by itself, it's a pointer to the address where this first element is stored. Right? So we'll see that the address of alphabet and the address of the first array element, so if I say address of alphabet, just the array name, or address of alphabet at index 0, both of those names, both of those addresses point to the same location. Right? And we can see that then, actually then, memory example 3.c that you're given with a lecture material. Right, let's take a look at this example here. All right, so here's our array. Now, in this case, actually, let's go back and let's just make this the char array in that example of the previous slide. All right. We could do it with ants. We'll turn around and do it with ants again in a second. B and D. All right. So there's an array here. If I name this alphabet, all right, I have to name this alphabet. And this alphabet, and this alphabet. All right, so what we're going to do is I'm just going to print out addresses. Remember, we use %p with pointer. So if I just use the name alphabet all by itself in this printf statement, we're going to see that we get the same thing as if we use the address of alphabet or we use the address of alphabet 0. So let's build and run. And oh, well, not if I don't spell it correctly. And I should have done just a find and replace here to be consistent, and here in our output, our alphabet at address 0. Now let's build and run. All right. And I should have another space in here, but we can see that the address, so the name alphabet, right, just using that name with %p, the address of alphabet or the address of alphabet at index 0, all 3 of those refer to the same address location. Right? And that's what we mean when we say the name of an array is a pointer to the start of the array. So the name of the array is a pointer to the start of the array. Right? Similarly, if I went back and undid all these changes to our array, back to the example that you're given here, right? Changes back to 1, 2, 3 here. And lastly, the data type back to int. All right, here's your original example. So now I made an array named array. It's got 4 elements. They're all of data type int. The numbers 0, 1, 2, and 3 are stored in the array. And we'll see that when we use the name array, or we use address array, or address array at index 0, they all produce the same address. It does not matter what the data type of this is, right? They all produce the same address. Name of the array is a pointer to an array address. And we've seen that as we've been passing arrays and functions that we've been able to change memory in other locations. All right. So we want to remember then that memory is placed on the stack from higher to lower addresses. Now going back to this example where we've discussed this previously, right? If X is the first thing declared, then in the scope of memory, right, X is placed out on the stack. So I use 4000 as the high address. So X is placed out there, and I'm assuming my integers are 32 bits, so 4 bytes away, right? Remember, memory addresses correspond to byte addresses. So Y would be 4 bytes away at 3996. So here I'm showing the variable name, the memory content, and my memory address, right? And then 4 bytes away from that, we should store CC, variable CC, which is of type char, right? It will be initialized, that memory space will be initialized to the character A. It only takes up 1 byte memory, right? A char is 8 bits, so it takes up 1 byte. Right. Now I'm going to create a pointer, right? A pointer to a char. So star PC, so the star here says declare PC as a pointer to type char. Right. I'm going to store the address of CC in PC. Well, the address of CC is 3992. You can see that PC stored in its memory has 3992. And then I'm going to store the float F next in memory. In this case, it has 3.14. All right. Now, in the same way that we store an array in memory, right? If I create this array, this character array here, right, A, it has 4 elements. A at index 0 is stored at the lowest address. So what this does is it knows that it needs 4 bytes for 4 chars, right? If the next available is 4000, it's going to store A at index 3, the end of the array, at 4000. The base of the array, then A at index 0 is 3997. So it places these at lower addresses, right? Remember, we go from high to low. And the thing is the index then is an offset location from the base index. If I use the name A all by itself, A refers to this memory address of 3997. So A at index 0, that's a 0 byte offset from this memory, right? A at index 1 is a 1 byte offset. A at index 2 is a 2 byte offset from the base. A at index 3 is a 3 byte offset from the base, right? This is going to become important when we start talking about pointer math. Right. And so we could go ahead and write a program. Let's open up memory example 4. It's just a program that's just going to display the address of each memory location of the array element. All right. So let me open that up here. Add this to the project, and then I'll remove this file from the project. All right, so 4 is in there. Clean out that workspace. Let's build and run. All right, let's take a look at the output. So the output here shows us the address of each array element. Right, so I've declared now this array of type char. It has 4 elements. We stored A, B, C, and D in there. Right, now I'm just walking through the array. I'm starting at index 0, right? I'm using I as the index. So array at index 0, when I is 0. That address, well, to get the address of that, I have to say the address of array at index I. That gives me the address of that specific location. Right, so we can see then at 0, the base address is 0028FF08. The next address is 09, 0A, 0B. They're all 1 byte apart because the size of an int is 1 byte, right? If we use it, I'm sorry, the size of a char is 1 byte. If we use the size of operator, size of a char data type is 1 byte. All right, so this is just a way to walk through the array and show what the addresses are. All right, now, if we were to change this, right, what if we change this data type to int? Right, I can still store these char representations in an int. Right. If I build and run now, right. So the base address of index 0 is 28FEFC. The next one is 0, 0, right, which is 4 bytes away. Then this is 4 bytes away, then this is 4 bytes away, simply because my int takes up 4 bytes on my system. All right. Now, normally we use chars to store char data types, so if you think that might have been an issue because I'm using the chars, let's just go back to our numbers 0, 1, 2, and 3, where we know the data types are ints here. All right. All right. And once again, I'm just printing out the addresses, not what's actually stored in the array. You can see we get the same sets of address, right? So the important thing is the name array, right, is a pointer to the base or the start of the array. The index is an offset of how many bytes away. Well, for a char, we saw that each one of these indices indicated how many bytes away, right? Address 1 was 1 byte away for a char, but for an int, index 1 is 4 bytes away, 1 integer away. Index 2 is 2 integers away, or 8 bytes away. Index 3 is 3 integers away, or 3 times 4, 12 bytes away. Right? So there's a little bit of pointer math going on there, address math going on. All right. All right, so that example showed you how to see the address of the individual array elements. All right. Let's go ahead and take a look at memory example 5 here. And add it into our project. All right. I'm going to use the array name as a pointer here, and then I'm going to read and write the first array element. So the read operation here. All right, so here's A, right? A is an array of 4 integers. We stored the values 0, 1, 2, and 3 in there. Let's just do a run to cursor here. All right, so if we open up A, we can see then 0, 1, 2, and 3 is stored in A's memory. All right, now, if I want to print out the first value stored in the array, if I use the indirection operator with the name of the array, so there's the indirection operator with the name of the array, that's the same thing as saying A at index 0. And I'm also going to use A at index 0 here so that we can see that when we read, right, they're both going to refer to the same location. So, next line, right, and then next line here. Popping this up, right? So the first value is stored in the array named A. So when I use the indirection operator with A, so when I dereference A, that's the same thing as saying, return to me what's stored at A at index 0. Well, A at index 0 has the number 0 turned in it. When we use the index notation, A at index 0, well, it returns what's stored. The value stored at A at index 0, in this case, happens to be 0. Now, if I want to overwrite what's stored at A at index 0, I know then I could write A at index 0, assign to that the value of -7. But instead, I'm going to use the indirection operator here. And I'm going to say assign -7 to where A points. Well, A points to the start of my array. Right, so next line, notice then A at index 0 is overwritten. And if we were to execute this printf, right, pop that up, we'd see it prints out the changed value. So we can use then the array name to refer to locations in the array, right? When we use then the array, if I use the indirection operator with the array name, that is the same thing as saying A at index 0. So the name of the array points to the start of the array, the first element in the array. All right, now, array names are constant pointers, right? We can't change where they point to. So they are a pointer, but it's a constant pointer. We can't declare an array and then have it point somewhere else, right? We can assign other pointers to point to the array. So let's look at this example. All right, here's what we did before. We have this array named A. We initialized it to these values. Then this array has 4 ints in it, so 4 values of type int. So if I want to make another pointer point to this, I need to make a pointer to an int. So star PTR declares this variable name PTR as a pointer to an integer data type. And now I'm just assigning A to this. So since A is the address of the start of the array, right, I'm making PTR point to this array. It's the same as PTR equals address of A, or the same as PTR, assign to PTR the address of array at index 0. Right? But what I can't do is I can't turn around, even though in this case PTR points to A, I can't turn around and say, oh, let's assign PTR to A. That's illegal. I can't make A point to anything else. When we use the name A to declare it as the name of an array here like this, it points to this area of memory for the entire program. We can't make it point to anything else. Right? And I can't make A point to another array either. So if I have this array B, right, that's 4n, same data type as A, and if I make some pointer Q and assign it to point to B, so Q points to B, I can't say, well, now let's make A point to B simply by trying to assign Q to it. In other words, once we create an array, we can't make it point to anything else. Right? So array names aren't quite the same as pointers. They're a pointer to constant area of memory. But we'll be able to use these as arguments to function calls to pass pointers to arrays. Right, now that we've talked about arrays and that notation a little bit, let's talk about pointer math, right? Pointer arithmetic. So we can use integer addition and subtraction with pointers. Right? We don't use pointer math with floating point types. In other words, I don't take a pointer and add 1.23 to it, right? I can add, remember, pointers point to memory, and memory are address locations or whole numbers. So it only makes sense that we can add other integers, other whole numbers to it, right? I can add 2, I can add 3, I can add other integers, I can subtract from pointer addresses. I just can't add, we just don't add, subtract floating point constants, right? So what happens when we add 1 to a pointer? It performs what we call pointer math. And it depends on the data type, right, of how many bytes away. So we have some pointers. So when we say pointer plus 1, what's really happening behind the scenes is we're adding 1 times the size, one times the size of the pointer's data type. Right? So if the pointer's data type is int, and int is 4 bytes, that's like saying pointer plus 4, right? 1 times 4. And if I say pointer minus 1, well, that's minus 1 times the size of the pointer's data type. So if my data type is a char, right? If it's a pointer to a char, then it's going to subtract 1 byte. If it's a pointer to a char and I'm adding 1, that's going to add 1 byte. Like I said, we don't always have to do 1. We can use other numbers, 2, 3, 4, other integer numbers, right? So the important thing about pointer arithmetic is know that when you add 1 to it, it's not going to point just to an address 1 byte away. It's always this integer constant times the size of whatever number of bytes this returns based on the data type. Right. All right, so let's take a look at this example. All right, so we've got some variables. X and Y are just, X, Y, and Z are ordinary integers, and they've been initialized to these values. So here's X, Y, and Z here, right? X, then, since it was declared first, it's stored at memory address 4000. Y is stored at 3996, and Z is stored at 3992. Here are their memory contents. The last thing then, the next thing is P was declared as a pointer to an integer data type. Right, so here's P in memory. It got the address then at 3988. And then we assign Z's address to it. Well, Z's address was 3992. So stored in P's memory is the value 3992. So now if we say P equals P plus 1, that's the same as, let's assign to P plus 1 times the size of an int. Well, an int is 4 bytes, so the math here is what's stored now in P is 3992. That's where this comes from, plus 1 times 4. So assume size of an int is 4 bytes equals 3996. So P now will point to Y simply by performing this math. Right. And now similarly, right, in this example, we have the same X, Y, and Z, but now we're going to make P point to the address of X. So X's address is 4000. We can see that we store 4000 in P's memory content. And now when we say P minus 1, Well, P is 4,000, that's where this comes from, minus 1. Well, it's 1 times the size of an int, right? So 1 times the size of an int. This is based on the P's data type. P points to an int, so 1 times the size of an int, right? And now we'll make then by the subtraction, instead of pointing to X, P now points to Y. Right? So pointer math then relates to the data type that points to, and when we add and subtract from it, it's based on the number of bytes of that data type. Now you can do things like this. You can do these sorts of math operations, right? Like I said, we can add 2. We can say P++. So that's just simply the same as adding 1 to P. But remember, there's pre-decrement and post-decrement, right? So you have to be aware of how it's going to affect. If you're just using it like this, P++, plus P, we're just going to end up adding 1. We're going to make P point to the next area of memory that many bytes away, right? But if we're subtracting, right, we go the other direction in memory, and it's useful then for walking through arrays. That's our idea behind here, is that we're going to use pointer math, end up walking through arrays. Because it doesn't make a whole lot of sense to walk through data like this. We have to know exactly how our data is structured. We use the pointer math with arrays so that we can stop using the index notation and start using the array notation to walk through the arrays. Right. Here's another example then. If we have X that we declare right in memory and store 5 in its data, and now we declare pointer X is a pointer to an integer data type, that's this declaration, and then we assign to it the address of X. So the address then of X is stored in pointer X's memory. That's what happens here with this line. Now when we say pointer X plus plus, well, that's add 1 times the size of an int, right? So 1 times 4 is added. So in this case, if this has 4,000, that says take 4,000 and add 4 bytes to it. This would now point to 4,004. And now if I say minus equal 2, well, that's 2 times the size of an int. So 2 times 4 bytes is 8. So if I take 8 away from 4,004, we point back to this address. Like I said, just doing this exercise here, we wouldn't do in a program. We're going to use it with arrays. But it's important for you to realize that we're advancing a certain number of bytes away in memory. All right, and there's an example program, right, pointer math 3, that you can run and take a look at the results of what those additions and subtractions perform for you. Pointer math 4 as well with a different data type. So go ahead and run that, take a look at that. Right, here's where you want to be careful then when you're using the indirection operator and doing incrementing or decrementing at any time. These two expressions are equivalent to each other. What this means is this says, go ahead. So the indirection operator is taking precedence. Read the value where P points. So this is post increment. Remember, post have increments after. So this is go ahead and read the value where P points, return the value that was read, and then make P point to a different address. Right. So the value of the expression is star P before the increment, and then it increments after, just like the post increment that we know. It's returning what's in memory before it increments. All right, you can write it like this too, that this works similarly to the one above. All right. Now, if you look at this, this looks very confusing. To me, this looks a little less confusing. This looks even less confusing by putting the parentheses. Actually, if you put the parentheses around this, this looks like it's forcing order. And if you think about it, then post increment means return what's in memory. So this returns what's in memory, and then it adds 1. So before it makes P point to something else, it returns the memory where P is currently pointing. Like I said, these can be a little bit confusing of how they work, right? In this case, this is actually going to make P point to another memory location before it returns what's there, right? So you need to be careful with these. If you use them, to me, using an expression like P equals P plus 1 is it's much more clear of when I'm performing the math and when using the indirection operator. So you can use these if you want. I'll probably not use them in too many programming examples in class just because they're a little more difficult to remember. There is an example problem then that you can run to see the different results that it gives you. Our next lecture then will be using pointers to access array elements.